Hi everyone, it's great to see everyone on this call. Today we're going to look at something that's maybe a little more technical than we've looked at in the past. MDCD ratio. On the paper machine, we'd probably see that as some sort of rush drag setting. And what I want to talk to you about today is the important things associated with rush drag as it relates to how you develop and generate properties. So before we start, let's see if we can make sure everyone's able to tune in and hear us properly. So we'll just wait for a few seconds and make sure the tech's working properly. Okay, well, that sounds good. Let us know if you're having problems, and Ashley will sort them all out for you, I'm sure. Now, the thing about rush drag, MDCD ratio, and setting it is that often they're not completely related. It's a complicated subject. So this presentation is a little more technical than we would normally do and a little more wordy, but stay with it. It's worth understanding because it gives you some insights into how to run the paper machine. The other thing that's happening is that by running the paper machine in an uninformed way, you're losing money. I want to talk to you about that as well and how we can get it back for you. So let's kick off and see how we go. It's worth revisiting this slide, which was to look at what property variation on the paper machine is costing you at the moment. So this is the money lost due to lack of quality control, and it's an indicative sort of rate. And the first thing is lack of control of quality costs you probably on a 250,000 tonne paper machine, high reject levels, $0.6 million, $600,000 a year lost because you can't really know what the quality coming off the paper machine is like. The second thing is, if you can get quality under control, you have options and flexibility. So you can drop the basis weight a few grams, you can use less expensive inputs or less inputs in general. And typically we find that there's about $1 million saving in that. If you're a starch recycle machine, and we're looking at some interesting work at the moment, adding starch to kraft linerboard machines with some recycled in it, and there's some exciting things coming forward from that. But at the moment, if you're just a 100% recycled paper machine, there's about a $1.25 million saving from that. Using less expensive furnishes, maybe refining less. I mean, the advantage of refining less, of course, is that you get better freeness or better drainage, and your production rate often increases. And then finally, the big one, if you can take some grams off the paper that you're using but still get the minimum performance, then you're looking at typically a whopping $10 million a year. That's well worth traveling and following. So that's the size of the prize. Let's do some technical talk. The first thing is MDCD ratio. In our terms, we're thinking about the property in the paper sheet, not the rush drag setting, because often they're not related and people don't always understand this. So poor control of MDCD ratio has the potential to increase fiber orientation problems. That's problems in the corrugating plant with warp, curl and things like that. It can increase forming instability that already exists on the paper machine, and we'll talk briefly about that. It ensures that any paper you make has to be overspecified. It has to be more expensive than you really need it to meet your minimum requirement. And finally, if you're trying to design grades, if you're trying to balance different properties, and Aurelia know a lot about how the different properties are created and developed, if you're trying to make strategic product development and control, well, if you've got variable MDCD ratios, that's nearly impossible to achieve. If you're trying to, for instance, balance good burst with high CD/SCT, and you have a lot of changes in your MDCD ratio, then you're going to really struggle to get an optimal solution. So let's start with some definitions. And I have to say to you, I get confused as well. When you're not dealing with drag and rush, the definitions can be quite difficult. Well, here's one. The velocity at which the jet is emitted from the slice compared to the wire speed determines the rush or the drag. And if the jet velocity is less than the wire speed, that's called drag. And if the jet velocity is greater than the wire speed, it's called rush. And really, it sounds like it's defined from the point of view of the fiber landing on the wire. So if the fiber is faster than the wire, it tumbles and rushes onto it. That's how I think of it. It can be very confusing, though, for those who aren't using those terms every day. But we do know some things about rush and drag. Firstly, that the fiber, it only experiences the relative velocity. So a reject rush wire speed ratio of 1.02 might be 20 meters jet wire speed difference at 1,000 meters a minute and 30 meters difference at 1,500 meters a minute. That means you can't leave your MDCD ratio at the same setting if you're changing your machine speed. You must always think about it in terms of the difference between the jet and the wire speed. Most paper makers will know that, but it's good for the rest of us to understand it as well. So the big learning from that is that the same sheet properties are obtained at the same jet wire speed difference, not the ratio. And it's the difference that we're concerned with, because the difference helps set the MDCD ratios, and the MDCD ratios help set the properties that we end up with in the paper. So jet velocity less than wire speed is drag, jet velocity greater than wire speed is rush. And here's a plot showing the tensile ratio that's developed at drag and rush. And you can see that when the jet to wire difference is around 0, then we get a minimum in the tensile MDCD ratio. So the sheet's as square as it's going to be at that setting. As we move either side of 0 difference, we increase our tensile ratio MDCD and our properties change. So although it might not be important to operate at a particular point on this curve, it's very important that we know what the curve looks like and where we are operating. So some observations from the work that we do on paper machines with our continuous PSM4 measurement. Firstly, measuring the speed of the jet is nearly universally difficult. The measurement can change with jet speed and flow box pressure. So it's very hard to know where you are in terms of rush drag and the resulting effect on the paper as well. This is where the PSM4 provides a good advantage, because what we see there is that the measurement gives us the properties in real time. The MDCD tensile ratio is mostly set in the forming section. Well, paper makers will know that. But there's some other things that happen. MDCD tensile ratio, and that's what we're interested in. We're interested in the properties that are developed. They can also be altered by changing the fiber length. Shorter fiber length means that your MDCD ratio decreases. If you have cross-machine shrinkage during drying, which a lot of older machines would have, if you re-wet into and out of a size press, that can change the MDCD ratio. Changing section draw tensions at particular moistures can very much change the MDCD ratio by changing the MD and minimizing the CD. Orientation of fibers into the thickness direction of the sheet is another way that the MDCD ratio can change. And finally, just changing a grade or changing the machine speed, if the settings for the MDCD or brush drag ratio settings haven't been changed, they will change your MDCD ratio and properties. The other thing to be aware of is, and it's a bit of a myth, is that if you have increasing fiber orientation angle, that somehow the MDCD tensile ratio is also going to change. No, it isn't. Not very much. Don't worry about it. And the other thing that's of interest is the observation that in most cases, when you change MDCD ratios, the geometric mean of the properties that you're changing remain pretty constant as a measure of the sheet quality on that particular machine. So it's a valuable thing to measure, the geometric tensile ratio. Okay, hopefully they were some points of interest for you. Let's look at how we get our MDCD ratios when we change rush drag, the way the fibre hits the wire and the way it travels with the wire. Here's one way of looking at it. The vertical blue axis is the jet wire speed difference. So we're going to look at it as a vector problem. And on the forming table, we have lateral flows. Most of these flows are flows that we're not really wanting. Some of them are to help with the quality of the sheet, but some of them are just there because hydraulic systems aren't perfect. And you can see that the resulting angle from the two vectors, which is the red arrow, it goes off at an angle. It's the result of those two hydraulic effects. Now, if a jet to wire difference becomes smaller, that is to say, if we make the sheet squarer, then we get this result. Lateral flows are exactly the same. All that's happened is that our jet wire speed difference has decreased, and all of a sudden the angle of the fibres has nearly doubled in this example. So what that means is changing jet wire speed differences can cause problems with fibre orientation angles on the machine, and you have to be careful with it. Now, do we see this sort of effect in practice? Well, typically not, because we can't really measure it. But if you had a PSM4 on your machine, then this is the sort of thing you'd see as the sheet is squared up. Now, this looks like an interesting plot. It's a rush drag trial, and the blue dots and lines are test room results, top of reel, and the red line, the continuous line, is the PSM4 output. And the thing I want to draw your attention to is we range from about 2.3 down to about 1.8. And as we become squarer, look what happens to the fast noise or the fast variation in tensile ratio. It starts to get higher. I can plot this slightly differently, which might make it a little clearer. On that top plot is the plot we were just looking at, the chart showing how we've changed MDCD tensile ratio. On the bottom plot, the blue dots represent the peak-to-peak variation that we see in MDCD ratio as we square the sheet. And you can see that we go from about perhaps 1% variation, and as we square the sheet, our variation goes up to 5. Well, in actual fact, the way this is plotted, you can double that. So by the time we get to about, say, 1.7 in terms of an MDCD ratio in the paper, we have variation in MDCD values of around 10%. Now that's a lot because that directly affects our quality. Here's some other things that happen with paper properties, and I want to look at paper properties now because we're going to look at how the MDCD ratio affects them. It's important to understand that and how sensitive different properties are because they're all different. And here's an example. This is an example of a sheet being changed by 50 GSM. And what I've done is plotted different properties and shown how much that 50 GSM addition, there's been no other change, how that 50 GSM addition changes the property. And you can see that depending on the property, ring crush, for instance, nearly more than doubles, whereas Scott ply bond hardly changes at all, and tensile has very small changes. So it's important to realize that different properties will respond differently to changes that you make. Now let's get back to our MDCD issue. So here's an example um, an observation we can make. Let's imagine that I have a paper that has an MDCD tensile ratio of 2.5. And I really should have hidden all these other bars and given you a chance to guess what would happen. But let's look at other properties. So for the same piece of paper that has a tensile ratio of 2.5, let's look at what happens to other properties in terms of their MDCD ratios. So extensional stiffness, very close to the same value. TSI, tensile stiffness index, also very close to the same value. Now look at SCT. The CD tensile ratio only gives an SCT MDCD ratio of 1.7. Ring crush, 1.4. Work, 1.2. And stretch, 0.6. Goes the other way. Really just trying to say different properties will respond differently to changes in MDCD ratio in the paper. So we need to understand when we're trying to optimize different properties, what sort of sensitivities and changes can be made. So in summary, the MDCD ratio of the paper directly affects paper properties, but it varies depending upon the property. The jet to wire difference is largely irrelevant. In terms of paper quality, it's largely irrelevant. But we do need to find a jet wire difference setting that optimizes MDCD ratio and gives the best set of properties while still maintaining good runnability on the paper machine. Running squarer invites variability and fiber orientation issues. It's important to know how your machine runs when it starts to become squarer. What we don't want is variation that we can't measure top of reel, but that's still there and increasing, because what that means is that over time you have to over-specify the paper performance. And finally, properties have different sensitivities to MDCD ratio. So for example, if I wanted to optimize burst, I could do that, and it's very sensitive to changes in MDCD ratio. But CD ring crush is not so sensitive, so what should I do? Well, probably the best strategy would be to concentrate on changing burst and then look to the CD ring crush not changing or changing only half as much. So it's important to know which properties are sensitive to the changes you make. Okay, now we're going to look at some 4 areas that we would normally look at, Aurelia's PSM4, and when we're doing projects around these sort of areas. And the first thing is sensitivity analysis. So how sensitive are properties to changing MDCD ratio? And I should point out that these are really like mechanical engineering properties. So if you change the MDCD ratio to a certain extent, then it will follow that you will get these types of changes in different properties because they're mechanically related, physically related, and structurally related. I hope that makes sense because it's an important point. So if we introduced a 1-point MDCD tensile, that's a unit change. So if we went from 2 to 3 in our MDCD ratio, the question we want to ask is, what would happen to the properties that we're looking at? And here's a few examples. So for instance, if we increased the MDCD ratio, so made the sheet more oriented, we would lose about 9% CD ring crush. We would gain about 9% stretch. We would gain about 21% concora, 16% burst, and we would lose CD, STFI, or SCT by about 11%. So what that means, of course, is that if I'm trying to optimize burst, it's unlikely just using MDCD ratio that I can also optimize CD, SCT, or CD ring crush. But knowing the sensitivities of different properties, we can put a strategy in place to give us the best result. This is a slide we showed at the last webinar. It's important because it still holds now for this discussion. We find there are really 4 categories of variation on the paper machine in terms of quality and performance. There's fast, non-periodic changes, there's fast periodic changes, slow non-periodic, and slow periodic. And this is roughly how we found that they're divided up. What we would like to do, of course, is remove this variation, because if we can remove the variation, we can lower aims, use less expensive materials and inputs, and save money. New capital equipment, hardware maintenance, fast, non-periodic, around 1/3 of the variability on the paper machine is like that. Slow and non-periodic, that means that we can actually attack it with something like an online strength sensor, is around half the variation that we see. 8% is fast and periodic, which means that our project groups can attack that. And then the final category is slow and periodic. And again, we need project groups to look at that, come to some conclusion and minimize it. So it's just worth seeing the size or the division of how variation on quality on the paper machine occurs. So what does it all mean for us? Now here's some examples, some real examples of paper machines. In this case, it's a recycled medium machine from Europe, and I'm showing you the MD tensile ratio for a sequence of reels, 700 reels in this instance. And what it's telling us is that there is a very large variation in MDCD tensile ratio, and that very large variation delivers a 25% variation in Concora. Now, as it's a medium machine, it's trying to develop Concora as a general test. Concora is important to it, and yet they have a 25% variation. And what that has to mean is that they're over-specifying the paper for any application that they use. Here's another example. This is a Kraft sack machine. In Kraft sack machine, the work energy is really important. This is a PSM4 trace, a continuous trace over what looks to be about 3 days. And you can see there's a slow general trend down from 2.8 down to 1.8. And then all of a sudden it's realized that, hey, we're letting this get away from us, and they recover slightly. That sort of trend in MDCD ratio is worth about 20% variation in work, which is one of their primary measures on that machine. Here's another example, a Kraft linerboard from the USA. Again, lots of variation in MDCD ratio, unwarranted, and this would deliver a 10% change in CD ring crush and a 20% change in burst. So not having control of the MDCD tensile ratio of the paper immediately translates into variation, unwanted variation in performance of properties that you are really interested in. So what can we do about it? Well, the PSM4 measures TSI, and you can see here a plot of modulus, tensile and extensional stiffness ratio, and you can see that in general they really follow each other very well. The closest we come to in our measurement is TSI, tensile stiffness index, which is really an analog of extensional stiffness. So I really threw this plot up just to show you that as the speed difference changes along the bottom there, they're tracking the tensile ratios pretty well, and that's why we can use it for this sort of work, use the PSM4 for this sort of work. Here's another example of jet to wire differences, and you can see along the bottom axis the SCT that was predicted as the jet to wire was changed, and also the measured, and it's a very, very good relationship. So we can track changes in property as in real time with the PSM4 as the jet to wire difference has changed. So what does it mean? Well, what it means is, for instance, in this case, which was a European 100% recycled paper machine, no, Australasian, is that you can be running with lots of variability. If you're not measuring it, your variability will remain and it will affect your product quality. Now, in this case, that sudden drop at around the 2nd of August, 0208, that's worth about 3 to 4% SCT. So they are introducing and injecting an additional requirement for 2 to 3% SCT in every bit of paper they made off this machine. Once we started to see that and control it back down from, say, 2.5 down to 2, that's worth 3 to 5% in compression strength. Now, you can take that either as a better quality sheet, or you can take it as a way of getting cost out of your operation. Either way, very valuable observation and control available. Here's another example which I always throw up because I really like it. I like the colours. The MDCD ratio is in green, you can see that there, and matching it is the response from the CD SCT that was measured. This is a PSM4 example, in this case from a European recycled machine. So you can see that they're very closely related, and that largely when that very strong cyclic variation of around 12 minutes, in this case, was removed, then also so is the variation in the CD SCT. So you can see the relationship directly between MDCD tensile ratio and, or in this case, stiffness ratio, and properties like CD SCT. No one wants a 12-minute variation in SCT that's periodic like that, and that's worth 4 or 5% of the sheet value, of the sheet quality value. No one wants it. So let's go back and look at the money that we lose from not taking these sorts of things seriously and following through. This is unnecessary cost from not controlling and measuring the quality. High reject levels, 0.6 per million. Lower production rate, 1 million. More starch than you need, 1.25 million. More expensive furnish than you need, 1.75 million. And then the big one, an opportunity to get rid of grams out of your sheet and still perform at the minimum the customer expects. That's a whopping 10 million. So here's a clue as to how Aurelia goes about these sorts of projects and this sort of work. Firstly, a sensitivity analysis. So understand how the ratio affects sought after properties. Remember, it's not the jet to wire difference setting, it's what it does to the sheet that's important. Now, I know that's hard to find out if you're only measuring top of reel. Lots of noise, lots of variation. But that's where the PSM4 comes in handy, because it measures continuously. So you get trends and you can make changes and see them happen. The second thing is variation. Identify the level of variation on your machine and the cost of allowing it to continue, because that will drive the project forward. Now, if you're in doubt about this, or you don't believe what I'm saying, just plot the top of reel data for the last 6 months from your machine and your test room and see how it looks. And then translate it using the figures I've given you into differences in performance in properties you're interested in, and then put a price, a cost on it. And you'll see that it's worthwhile looking at this more closely. And then the third thing is try and get tools that will give you enough information to make the changes and then keep the changes, make the saving and then keep the saving. So in our case, we apply online measurement technology that we have developed that minimizes variation and optimizes the quality. So I'm going to leave you with this chart because hopefully it will drive some behavior and some thinking and some serious discussion about what might be possible on most paper machines that are running at the moment. So there you are. Hopefully it's giving you some information that's going to be useful. Hopefully it's giving you something to think about. And remember, we're always interested in talking to people about their problems, their issues, and how we might be able to save them. So hopefully till next time when we see you, have a great couple of months, probably a month, and then we'll see you as soon as we get back to it.